Hello, good morning, everyone. I'm Shweta Jain. I work at Intel. My current role is a silicon architecture engineer. And today I'll be presenting our work, which is offloading ScatterGather via custom accelerators on a COPA FPGA network platform. This is a collaborative work done within our team. I'll be presenting on the behalf of group today. So let's get started. The outline of today's talk is arranged as follows. I'll be going over the motivation of our work, why ScatterGather. I'll be also discussing the POC framework that we have in place, what we call is COPA, and the type of acceleration nodes that it supports. Next, I'll be discussing the gather scatter implementation and results in specific contexts to COPA. Finally, I'll be talking about the OFI support that we have put in place and conclude with our future work. That being said, let's get started. The primary why ScatterGather, why we chose this particular application. So the primary motivation of our work was to accelerate the most commonly used distributed programming constructs, which happen to be ScatterGather. And based on different workload studies that we did and just the general knowledge, state of the art that's out there, ScatterGather communication patterns tend to have a pretty high communication overhead, which impacts the overall performance of the application. So this seemed like a good nail for our hammer to take to. So that was one of the reasons to go with ScatterGather. What we want to do as part of this work is we want to leverage the highly customizable and high performant COPA framework that I'll be discussing shortly to design custom accelerator blocks for these constructs and then expose these enhanced implementation to the OFI upper layer application. So that's the big picture here that we are trying to address. So what is COPA? COPA is basically a short form for a configurable network platform accelerator, and it is basically a custom in-house customizable framework that integrates communication and computation on an FPGA platform. So the picture that I've shown here on the right hand side is basically showing what the entire COPA stack looks like, starting all the way from the application level, going down all the way down to the Ethernet layer, how the stack is organized, and we control most of it with it in-house with our design team. So what COPA does is it integrates FPGA as a smart NIC capable technology and functions as an autonomous node so that it can attach to off-the-shelf commodity network switches, or it can also be integrated in server type systems where it can be added via a PCI card. This communication protocol that's supported within COPA is RDMA based. So you can think of it as basically one-sided communication protocol that supports the typical RDMA constructs of puts, gets, and messages. We also, because we are working out of FPGA is basically our development platform here. We also try to support, we actually support custom acceleration capabilities within COPA. So and that can be exposed to the application middleware. The COPA software stack that we have developed is based on open standards, and it requires very minimal changes to be integrated as part of existing applications. So if existing applications want to leverage the COPA framework, the integration cost is fairly low, or the integration overhead is very low. The architecture that we have implemented for COPA is not only a scalable solution that is capable of deployment across multiple FPGA nodes and hence creating a very large distributed network, but it is also extremely high performant. We have published the COPA performance numbers as part of our previous work, previous publications. But the key takeaway here is COPA provides a very high bandwidth, low latency network performance at fraction of the FPGA hardware resource cost. So hopefully that's enough of a context of what the COPA is. This is the primary driving vehicle for this work. For the purpose of this talk, I will be primarily focusing on the accelerator capabilities of COPA and not much on the networking side of things. So when we coming up with the architecture specification for COPA, we realized that we had this beast of machine, which is basically the FPGA card that can also be used as a co-accelerator, and which is one of the more traditional uses of the FPGA device. So based on that, we decided to support acceleration also as part of the COPA architecture. So we primarily support two types of acceleration modes in COPA. And these end up supporting actually pretty wide domain of applications. So we cast a pretty wide net by supporting these two types of acceleration nodes in our architecture. The first one that we call as the inline mode of acceleration is actually a very tightly coupled accelerator block that sits within the COPA networking stack. This particular acceleration mode or accelerator block is primarily targeted towards applications which have fairly low compute overhead or are streaming in nature. So we are basically with this mode of acceleration, we are able to provide uh, uh, acceleration and computation capabilities close to network speed. So case in point being, you want to append CRC or checksum or some kind of parity encoding on your incoming data packet or outgoing data packet. You can do that via the inline accelerator mode because it pretty much performs computation at network speed. So as the data is coming in, you can perform the computation. The second mode of accelerator that we support in our model is the look-aside accelerator. And this is a more traditional accelerator setup where actually the FPGA modules act like a co-accelerator. So we are basically decoupling computation and communication in the look-aside mode of things. The computation is performed by the accelerator block, but the communication or the look-aside accelerator block, but the communication and data movement is actually offloaded to COPA. So say you want to in a distributed system, you want to pull data or push data from a different node and then perform some computation on it, you would use a look-aside accelerator block depending upon the nature of computation. So because we have these two accelerator blocks support in our design, we have a key metric to distinguish what kind of capabilities we want to push in look-aside accelerate as part of look-aside accelerator blocks and what we want to push into inline accelerator block. And the key distinguishing factor is any application or any computation which is more compute intensive or have longer latency tasks like say matrix operations or lookup operations which are uh, which are fairly compute intensive or have a pretty long turnaround time. We don't want it to be part of our networking data path because what happens is from an architecture and system point of view, we never want to deteriorate the performance of our main networking data path. So what you would do in case of say a lookup operation is you will perform the lookup operation on a look-aside block while the networking path keeps making progress. So from a system point of view, we never want to deteriorate. We never want to introduce any kind of acceleration operation that will deteriorate the performance of our networking data path. So I hope that distinction makes sense. Uh, along with the COPA remote triggered COPA, the two modes of operation that are supported, we also have something called as COPA remote triggered acceleration. And this is basically supported in both the inline accelerator mode and COPA look-aside accelerator mode. So what is happening is we have the inline accelerator commands and the look-aside accelerator commands. Both tend to within command format, we have some fields which basically can invoke the accelerator without any involvement of the host system. So you can perform communication, computation independently, and that's what we kind of show in the picture on the right. On the left side, you can see it is the more traditional flow where the CPU is going to invoke the acceleration operation, perform some kind of data movement, and then accordingly write the results out and things like that. So there's always intervention from the CPU coming in here. In the remote triggered operation, the accelerator block can function completely independently. So what this buys us is it basically makes COPA act as a headless node. So it could essentially hang off a switch port or be an integral part of the switch further enhancing its smart NIC capability. So this is a pretty powerful mode of operation that we support in our setup. Moving on to the meat of the talk, which is basically gather scatter. I'll be starting out with the description for gather and then moving on to scatter. So just a brief description for gather, everyone here. No one needs it, but let's just discuss that. What the gather operation does is it coalesces multiple source buffers into a single payload and writes it out to a destination location. So that is what the gather operation is at a very high level. In our framework, this is basically COPA specific framework, we implement gather operation as an inline accelerator, and that is what we can see in the picture over here. We have a COPA initiator node which uses the inline gather accelerator to coalesce all the source buffers in its system memory. And then it uses the high performance network interconnect that COPA provides and pushes the data into the COPA target node's system memory. So that's what this picture demonstrates. The pushing operation is basically, the pushing operation to the system memory is basically a modified put or RDMA put operation that's happening. So this is all done at a line speed because this is an inline accelerator. So these are some further microarchitecture details that we have, like basically the nitty-gritties of how inline gather is supported in the COPA architecture. So the supported commands for performing a gather operation in COPA are put tree and message tree. They are pretty similar to the RDMA reliable put and message commands, and you can essentially think of them as same with an additional capability of gather operation that happens under the hood. From a microarchitecture standpoint, we have the batch buffer table that is shown in the picture at the top. And the batch buffer table is basically giving us the source and the length of the buffers that have to be coalesced. At the moment, it's only 256 entries deep, and the collective length of all the lengths in the batch buffer table cannot exceed 9 KB, which is basically the MTU size we support within COPA. So those are kind of the microarchitecture limitations for the design right now. So here are the benchmark results. This is a synthetic benchmark that we developed to get the gather results. So I'll briefly describe what the benchmark tries to do, and then we can look at the individual graphs that we have here. So the results for the inline gather acceleration are based on a POC benchmark, where the initiator COPA node gathers the data and pushes the payload to a target COPA node. So that is pretty much the flow that I described earlier also. So in the first graph, we are basically presenting a benchmark which has the source buffers arranged sequentially in the memory. The second graph that we have over here is for null data access. So basically, you still have the same batch buffer table that you had for the first graph, but in the second graph, the length for this batch buffer table is set to 0. So basically, you are not performing any gather operation, and this particular metric we have in place just to see the overhead of actually just fetching the batch buffer table, how much it actually adds to the overall computation or overall operation, sorry. So that is what the second graph represents. The last graph that we have here shows comparison between when the source buffer addresses are placed sequentially in memory versus when they are placed randomly in memory. So that is what the last graph is representing. So let's look at the first graph more closely, right? What it's trying to indicate. So in the first graph, we see the blue bar, and that represents basically a single DMA engine that is present in the inline accelerator. So inline accelerator can perform a single read operation at a time. And the orange bar represents when you have two DMA engines present in the inline accelerator. And we see for the orange bar, the performance actually dramatically improves. We are actually close to the pretty close to the network bandwidth for the last when the lengths are set to 256. So what's happening here is basically we when we have a single DMA engine, we fetch the batch buffer table from memory, perform the gather operation in the inline accelerator, and write out the data. And then again, we move to the next batch buffer and start processing. So you have a large bubble in the design when you're pushing the data, so on and so forth. In the case of two DMA engines, what's happening is the next batch buffer table that's in the pipeline gets started to process by the second DMA engine. So we are basically alleviating this issue of having a large bubble in the design to fetch the batch buffer again by having a weak ordering model. So that is what it represents. Moving on to the last graph that we have in the design, this is basically showing the performance difference that's happening between sequentially and randomly placed source buffers in the memory. And it basically shows the performance deterioration when we have the source buffers placed randomly in memory, and it kind of highlights the DRAM open and DRAM rows or closing and opening of DRAM rows and the cost associated with that. So that's what this particular graph signifies. So moving on to the scatter operation. So the scatter operation, again, I'll just give a brief description. The scatter operation is basically used to distribute a single payload across multiple destination buffers. That is what scatter operation does at a very high level. In our particular COPA specific particular COPA specific implementation, we implement a scatter operation by doing a pull for the payload that we need to scatter from a COPA target node. So the initiator node basically issues a GET request, pulls the payload that it needs to scatter from the COPA target node system memory, and then scatters it into its memory. So that is what you can see here is your source buffer resides in the target node, and then you end up writing into the initiator node system memory to different destination buffers. So the difference between the scatter and the gather implementation is we implement scatter as a look-aside operation. And one of the reasons for that is when we have to scatter the data, we have to basically hold on to the payload that we have to scatter till the very end, till the very last destination buffer is being written to. So it's basically you're just popping the data from the destination buffer from the incoming payload and writing it to different destination buffers. What if we would have implemented it as an inline accelerator, we would have had to basically block the networking data path when this particular operation was being done. And as per our architecture requirements, which I had referred to earlier, we never want to deteriorate the performance of our networking data path. So that's why we have implemented scatter as a look-aside block. And basically, the network path gives us the payload that needs to be scattered. We store it in a staging buffer within the look-aside accelerator block, and the networking path can, from that point onwards, make progress because the look-aside accelerator is doing the scatter operation in background. So both of them can, from that point on, run independently. Here are some microarchitecture details of how the scatter operation is supported in our framework. We basically support scatter operation via a getV command. So it's pretty much how we had the gather command also as part of putv messaging. Getv is basically equivalent of RDMA get operation, performing a scatter operation in background. So that is what the getV operation indicates in COPA context. So here are the results of what scatter operation, the scatter synthetic benchmarks that we were running. So just to recap, what the POC does is it implements a scatter operation where the initiator node pulls the data from the target node via get operation and uses the look-aside accelerator to perform scatter operation on its memory. In both graphs, the graphs are slightly different here than gather. So I'll just give a give what the key basically here is for the graphs. In both the graphs, we have the green bar indicating the null data performance. So basically, in case of a null data case, the scatter length, the length over which you want to scatter the data is set to 0, and it only has a valid address associated with it. And the purple bar indicates when we do a scatter for an 8 kilobyte payload. So the null in case of the null data transfer, right, we are still doing a get, we are still pulling the data from the target node. We just don't end up scattering it. So that's a key difference here. Um, so in between the two graphs, it's basically when the destination, the difference is when the destination buffers are placed sequentially in memory versus when they are placed randomly in memory. So it was just to highlight again the DRAM opening and closing of the rows, how much overhead it actually introduces in the design. So that's what this indicates. So if you look at the green bar and purple bar in both the graphs, right, you can actually see when we are doing the actual scatter of the data, the performance actually significantly deteriorates. And we were actually looking at it for a long time, trying to understand, because for uh, for the green bar, right, where we are doing the null data transfer, we still get pretty good bandwidth performance. So what was the issue here? And based on our experimentations, right, and running different combinations of tests, what we found out is there is a fundamental issue with our FPGA card that we are using. So we are running all these tests on the Stratix S10 FPGA card. And on this particular FPGA card, we have very limited DDR memory bandwidth. So we are using the DDR to host the staging buffer where we store the payload that has been fetched from the remote node. And the other issue is the cost of accessing that staging buffer is also very high. So these two performance impediments really deteriorate our performance. The high penalty of accessing the staging buffer is associated with the fact that we cannot get this particular FPGA card to close design at higher clock frequency. So that is how the high penalty comes into play. We were able to actually run the exact same design on the newer Intel FPGA Agilex cards. We synthesized the design for the newer Intel FPGA Agilex cards. And what we found is we were able to close the exact same design without a single RTL line of change at 30% higher clock frequency, without any clocking optimizations, nothing. So it's definitely a platform issue for us at this point to get the performance going up. Once we move to the newer Agilex cards, we'll have a higher memory bandwidth system and higher operational clock frequency. So these numbers should definitely improve. Um, this is kind of the last graph results that I have here, and this is basically the combined scatter-gather flow. So in this particular case, what we are trying to do is we are gathering the data on an initiator node using the per-tree message reflows that we have in place. Once we do that, we basically post a remote trigger message, a remote trigger acceleration request on the target node so that it can scatter that pre-gathered data. It can scatter that pre-gathered data on its memory. So this is kind of combining all the accelerator modes of operation and the support that we have in place in a single benchmark. So that is what these graphs represent. We no surprises here in terms of performance. They pretty much mimic the scatter performance because that is the lower performant lower performant operation of the two operations. So it kind of follows the same trend. But we wanted to have this in place because we wanted to have a synthetic POC that serves as an example of what these flows how these flows will look like in context of applications, which is how they will be used. You won't use an individual gather or an individual scatter, right? You will be using them together in quite a lot of applications. So that is what we wanted this synthetic POC to indicate. Lastly, we have the OFI software extension. I'll just discuss pretty quickly about what we have in place. We have kept them pretty tight. We are accelerating the following OFI APIs. FI read message and write V. And the acceleration enhancements that we have in place are going to be agnostic to the middleware and upper layer applications. So you will not need any software changes to integrate, to basically use this. The scatter operation that we have in place is still going to be an optional support. It is not going to come as part of the default API integration, because when we ship out these COPA designs, for some of them we do have LA and some of them a look-aside accelerator, and for some of them we don't have. It just depends upon the end user's requirement. So this particular scatter support can be turned on and off via the middleware. Concluding with the future work, as I mentioned earlier, we are primarily focused on migrating all these functionalities to the Intel Agile X FPGA cards, which are going to provide significant performance improvements for both these operations. We are going to further use these enhanced constructs to develop an end-to-end application which is targeting matrix libraries like DGEM and SPGEM. These basically matrix operations rely very heavily on ScatterGather type of operations for data movement and consolidation. We also plan to demonstrate the viability of our approach in domain of high performance data analytics, where ScatterGather type of communication patterns are constantly used and actually incur pretty heavy performance penalties. So that is a pretty good domain to target. Our aim is to provide these commonly used applications with significant performance improvement with our framework. Thank you. Thank you for your time.
Cool. Thank you very much. We have a couple of questions queued up, if you don't mind.
Yeah, sure.
First of all, is COPA's RDMA following the Rocky V2 format, or is it Intel's own protocol?
So I would actually defer to my colleague Andre here. Andre, are you on call for this one? I think it is the typical RDMA, off-the-shelf RDMA that's available.
Okay. I don't know if Andre is. Oh, Andre, if you'd like to raise your hand, we can unmute you. Yeah, give me a second. Oh, there you are. There you are.
Yeah, we do use our own protocol. It's UDP-based, reliable datagram type protocol that we use for COPA. It's separate. It's on the lower levels than UEFI. It's between the two COPA cards.
Okay, cool. And then the other question, and another question is the staging buffer for the staging buffer, is the local memory on the FPGA, or is it on the DDR on the FPGA side?
It's on the DDR on the FPGA side, and that was kind of a design choice at that point. The way the hardware design is implemented at the moment is basically the networking data path DMA engines talk directly to either the DDR memory or the system memory. So and that is where the staging buffer is placed. So we don't bring it to the on-chip memory, but that will be basically the next step in our design.
I want to add that it depends on which staging buffer we're talking about.
This is for scatter, Andre, the staging buffer that we showed in scatter.
Right, but this is a problem. The placement reflects performance, and it's based on the hardware that we are using, the bandwidth and PCI crossing, PCI Express crossing, etc. So we did try it in several variations, but there are limitations with performance placing it in DDR with this specific platform.
Okay, thank you. And then the final question I have queued up, and again, I invite people. We have some time. What is the largest network? I'm sorry. Yeah, what is the target network line rate in gigabits per second?
Right now we have it at I think what we achieve is 12.5 gigs. That's in our current setup. That's the inline rate that we have.
So that's what the COPA system can support at the moment.
Yeah, yeah.
Okay.
Yeah, just to clarify, 12.5 gigabytes, not gigabits.
Gigabytes, yeah, sorry. Yeah, I said gigabytes. Yes, that's one.
Okay, cool. Are there any other questions? These are some good questions. Okay, I have no follow-up questions queued up for myself. Thank you very much, both of you. Thank you for that presentation, and thank you for the answers to the questions.
Thank you. Bye.